I've titled today's separations class, Accounting for Questionable Assumptions in Practice. Hopefully you're having fun drawing lines on the McCabe-Thiele diagram and learning how to design distillation columns by using the McCabe-Thiele analysis. But if you're like me, you're probably questioning whether or not engineers actually do this in industry. And I have to share that I've never heard of an engineer designing a distillation column by drawing lines on a graph. So today's class is again about rectifying what we learn in class versus what it is you'd actually do out in industry. And the first video is going to be a virtual plant tour. So I have a couple of YouTube videos that I'd like to show you to envision how a distillation column actually works. And by having a better visualization of how this works, hopefully we can get a better appreciation for how McCabe-Thiele analysis falls short. These are photographs of distillation columns out in the chemical plant. Appreciate their magnitude and their size. These things are absolutely huge in real life. This video is one of my absolute favorites. I'll show more about the different types of trays in a moment, but this is a look inside what I actually mean when I say a stage. So you can see liquid is flowing in from the stage above, while vapor flows up from the stage below. This is a valve type of tray. We'll talk about the different trays in a moment, but this is how vapor and liquid are actually contacting each other on each stage. These photos are from one of my MEB students in fall 2019. This is an extra credit project where he made a distillation column out in Minecraft. I thought this was really cool and a really neat visualization of how it works using the Minecraft world. This is a still image that kind of shows what we saw in the video and the different types of the stage. So each stage you can envision as like a plate, and each plate has a weir that holds liquid inside of each plate. So what's going on is liquid is flowing over the weir, and the weir is designed to be tall enough to hold enough liquid on each stage. So liquid is flowing into each stage over the weir and into the stage below. And vapor, because it's buoyant, is bubbling up through these valve caps, is what they're called. And that's how sufficient contact is being established between liquid and vapor phases. So these valve caps are designed to break the vapor into very tiny bubbles, and it's a frothy mixture in here with a lot of surface area for liquid and vapor to contact, and that's where mass transfer is occurring across the interface. These are the different types of column internals. So there's different types of trays that you may see. The simplest and least sophisticated are the bubble cap trays on the bottom. This is just a plate of stainless steel with holes in it that vapor can bubble up and through. The problem with the, these are sieve trays on the bottom, the ones with just the holes on them. The problem with this is that liquid can flow through the holes if the vapor flow rate isn't strong enough. So that could be a problem because then liquid is flowing to the stage below before it's reached equilibrium. So it's supposed to only flow to the stage below by overflowing from the weir, not by flowing in through the holes on the bottom. The middle level of sophistication is the valve type of trays, where the holes are a little bit smaller, and therefore the vapor flow can be a little bit faster through each one of these tiny holes. And also the vapor bubbles are smaller, and therefore there's more surface area for contact. While the valve trays are more sophisticated, they are more expensive as well. And the most expensive, but also probably the best for preventing weeping, as it's called, which we'll talk about in a second, are the bubble cap trays, which are on the top. So these prevent liquid from flowing down through the holes because they're a bubble cap, like the name implies, and vapor is flowing out through these slats in the sides of each bubble cap. So these videos are from the ECH Academy, and hopefully the sound will be able to play. I'm not sure if it'll be loud enough.
The animation shows a simplified two-component liquid phase with a 60-40 yellow to blue mole ratio. As heat is added to the closed system, a 9:1 yellow to blue mole ratio rises to the vapor phase. At equilibrium, the vapor phase is 80% yellow moles and 20% blue moles. The liquid phase is 40% yellow moles and 60% blue moles. At equilibrium, the temperature and pressure of both the liquid and vapor phases are the same. Additionally, the chemical potential of each component must be the same in the liquid and vapor phases.
So that last video was actually the wrong one. This was the one that I had intended to show. I'm not sure what happened with that last video.
Over the last 40 years. Liquid flows across the tray surface and vapor flows up through the tray holes. The area above the tray surface is a turbulent froth as the vapor and liquid mix. They are the simplest design and hence are relatively inexpensive. Vapor pressure drop is also minimal as there is no resistance to the vapor flow from valves or caps. Disadvantages include liquid weeping down through the holes and entrainment at high vapor rates. This results in a lower operating range.
This is a similar video, but for valve trays.
Valve trays, along with sieve trays, have dominated for the last 40 years. Valve trays generally are proprietary and contain movable valve units. When the vapor rate is low, the valve partially closes and minimizes weeping by restricting the liquid flow through the tray holes. At high vapor rates, the valves deflect the vapor flow. This reduces entrainment by creating a weaker vapor jet and results in a greater operation range. The valves do contribute to vapor pressure drop as the vapor must push the valve open.
And finally, the last video is on bubble cap trays.
The bubble cap tray was the most used device through the 1940s and early 1950s. An amazing number of them are still in service. The tray consists of a riser with a cap on the top. The vapor flows through the riser and around the cap and contacts the liquid as it flows across the tray. The one unique advantage of the bubble cap is that it provides positive assurance that there will be total vapor-liquid contacting without bypassing of the vapor. Their main drawbacks are due to the complex cap design. The caps present an obstruction to liquid flow, particularly in high liquid-loaded towers. Also, a large fraction of the vapor phase pressure drop is wasted, as it occurs in the reversal area between the riser and the cap, where it does not enhance the mass transfer. The labor cost of assembling the riser cap units makes these trays more expensive. The weight of these units also leads to support problems on large towers. Consequently, most new applications today are in services where a large amount of vapor must contact a relatively small amount of liquid.
I have just two more short videos to show you. This one is about weeping in a distillation column. So this is a term I've mentioned a couple times, and you might have heard it used a couple of times in the videos before.
An opposite performance problem occurs at low vapor rates, weeping. If the vapor velocity is low, it is possible for liquid to flow down through the tray holes before mixing the vapor. Weeping has been an important consideration in designing the different tray types. The potential is largest for sieve trays, which have no built-in protection against liquid draining through the holes. Valve trays can also weep, since the valve units are designed not to close completely at zero vapor rate. Bubble cap trays have considerable protection against weeping as one of their design strengths. Counterflow trays weep as part of the design.
And then the last term is flooding, or also known as entrainment.
Condition occurs when the froth level approaches the tray above. Flooding occurs at high vapor rates and results in a significantly lower efficiency. At these high vapor rates, the vapor carries much of the liquid up with it to the next tray. This recycling of the liquid is called entrainment. Entrainment mixes the stages together and reduces the countercurrent effect of the column. Flooded columns are also difficult, if not impossible, to control, as the separation performance will decrease dramatically.
So hopefully those videos give you a sense of appreciation that designing a distillation column is much more than drawing lines on a graph. And it's even more than figuring out how many stages you need or what the reflux ratio ought to be. You also have to design the diameter of the column, the height, the spacing of the trays, the material that they're made out of. There's many more considerations that unfortunately we don't have the time to cover in this class. But in the rest of this class, I want to talk about how we would account for the questionable assumptions that the trays are in equilibrium and that constant molar overflow is always being applicable.